Okay, so good morning, everyone. I must confess I had a little bit of trouble thinking on how to present this talk, because there are many people in the audience who know exactly everything I'm going to say, so it's going to be a little bit boring for them, I'm afraid. And the other half of the audience, I don't really know, what you don't know. So, okay, with the risk of boring everyone, I will try to be quite basic, at least at the beginning, and present the results that have been developed over many years on the dynamics, out of equilibrium dynamics of systems that also have a complex landscape, and in a sense the interplay between the interpretation of the dynamic solution that we obtain with methods that don't involve the landscape or don't use knowledge about the landscape, but how these results can be then understood or interpreted in terms of what we also know about the landscapes. Okay, so I, as I said, prepare this a little bit as a tutorial. I hope it's pedagogical and understandable. And the basic question that have worried some of us for many years is how does a large system reach equilibrium or not? And if it doesn't reach equilibrium, even over very long time evolutions, what does it do while it's evolving out of equilibrium? So basically, this is going to be the question that I want to be turning around all along my discussion today. And the way in which I want to address these questions, these two questions, is by starting with just a reminder of physical dynamics in one-dimensional energy landscapes, which will be very, very simple at the beginning and a little bit more complicated later on. And this is kind of, I like to call them the building blocks to then trying to understand how dynamics occurs in systems of many degrees of freedom, higher dimensional, and in energy or free energy landscapes in this case that will become increasingly complicated and complex depending on the kind of problems we focus on. So the second part will be about what I like to think is the simplest free energy landscape and the dynamics in that one. And then I will go to the complex cases and the cases of spin-glass models that we have already seen in many discussions, many talks in the beginning of the conference. And well, I will remind the definitions and so on and so forth. So in all cases, I will discuss timescales, I will discuss thermalization, and well, I will not discuss fluctuations, but I think they are important as well. Okay, so let me start from the beginning. So I will, as I said, begin talking about one-dimensional energy landscapes. So just the motion of a particle over a line with some potential energy on that one. So it's a physical problem, and the natural dynamics to start with is Newtonian dynamics for the particle. So I will say 2 words about Newton dynamics. It's not completely relevant in this context because, just this is an aside between parentheses, in other fields nowadays people worry about equilibration of closed systems, no contact with environments, and there the natural, of course, dynamics is Newtonian dynamics and their quantum extensions. So anyway, there is a reason to think about these problems that interest us also with Newtonian dynamics. But I will use it as the first step of my introduction only. Then I will go to dissipative dynamics, and the kind of dissipative dynamics I will discuss is Langevin. So it's the system coupled to a bath, and I will there discuss equilibrium versus out of equilibrium, white versus color noises, exponential versus non-exponential relaxations, and again relaxations, out of equilibrium diffusions, and activation processes, as I said, as building blocks to what will come next. Okay, so I start with a particle. It's moving on a line. Its position is written in my notes r of t. Velocity will be dot r of t, and acceleration double dot r of t. It has a mass m. This is the inertia term, if you wish, mass times acceleration. And then there will be some force acting on the particle. I write it time-dependent in general. And then I can make different choices for this force. So I can choose a force which is the derivative with respect to the position of a potential, V of r, and then I can choose the potential. In higher dimensions, I had other options, so forces which are not the variation, the gradient of a potential, and this will appear later in my talk. But for the moment, I only have this choice, let's say, for non-explicitly time-dependent forces in one dimension. But I also could put a generic time-dependent force, like, I don't know, some oscillatory force or forcing or anything I would like. But let's start by discussing the simplest problem, which is gradient descent in your terms, so derivative of a potential with respect to the coordinate. So Newtonian dynamics, what do we know? We know that energy is conserved under these conditions. So there is this quantity p squared. P now is mass times velocity squared divided by twice m plus the potential energy that is constant. So if I want to plot the evolution of my system in time in a picture like this, say for example taking the force to be the derivative of an harmonic well, then the particle will move between two extremes depending on which is the energy that I introduce with my initial conditions, and it will not go beyond. So there is constant energy, but there is also confinement. And the minimal and maximal values are given here in this sketch. Okay, so the potential I take to go to infinity, but this is not so important. What's important is that I'm at an energy which is below possible maximum value, which could be somewhere else. Okay, so I have confinement, I have constant energy. But now I want to mimic the coupling of this system to an environment. Okay? So the natural and simplest way to do this in the context of these kind of problems is to think in terms of Langevin dynamics. So these have been already mentioned in different talks. What does it imply? It implies that there will be two other terms added to this equation. One is friction, the other one is fluctuation, thermal noise. And usually one assumes that the bath doesn't have a memory. So otherwise stated, it's a white noise. And this means that there are no time delays in this friction term here. And moreover, it also means that the noise is delta correlated. So there is the delta function here and a prefactor that depends on temperature. So this is the prefactor that characterizes the temperature of the environment. Depends on the friction coefficient, gamma. And there is this factor 2 here that ensures that this bath that I'm choosing is in equilibrium. So there are ways to derive this. I'm not going to discuss it, just accept it. That if I fix this factor here in front of the correlation of the noise to be of this form, I am representing an equilibrium bath. Beta is, in my notation, will be the inverse. Oh, sorry, the -1 is missing here. So the inverse of the temperature, and okay, this is the usual Langevin equation. Now, if I want to do the same evolution of the particle within the same harmonic potential, and starting from some initial condition, what I know is that the energy will no longer be a constant. So there will be relaxation. The particle, in particular, will do some kind of noisy motion of this kind. This is just in a sketch. And that it will relax. And in particular, for example, the average of the position will go to the minimum of the potential with some functional form, some decay as a function of time, that for that problem can be very easily obtained. And it's an exponential decay. With timescales that depend on whether one considers a case in which one talks about overdamped dynamics. Basically, this term is irrelevant and can just simply be dropped. And then the characteristic timescale looks like this. While if this term is important and one has to keep it, the slowest, the characteristic timescale that will appear here takes a different form. Okay, so we still have confinement in the sense that the particle doesn't escape the potential when it goes to infinity at the borders, and we have no longer energy conservation. But we have more than that. So in this very simple problem, what one can prove is that due to the coupling to the bath, with the bath having this equilibrium property, this special relation between these two terms, the full probability distribution of both the momentum and the position of the particle as a function of time will approach, in the long-term limit, after these timescales that I mentioned before, a Gibbs-Boltzmann probability distribution, the usual equilibrium one, with e to the minus beta, the inverse temperature here, h, the Hamiltonian of the problem. And what's the Hamiltonian of the problem? It has a kinetic term, it has a potential term, and it has the usual form, and z is like a normalization constant. Okay, so the full description of, after these timescales, of the momenta and the position can be done with equilibrium techniques. And, I don't know, any kind of correlation function that you would like to compute, expectation value that we'd like to compute, you can do by assuming that after those timescales, the probability distribution reached this form, the usual form. Now, one can start complicating a little bit the form of the potential, so one can start, I guess, in your terms, using non-convex forms and putting a little barrier in between. And then in the Newtonian case, the energy is still conserved, and what the particle will do, where it will move, depends on what's the energy that you give with the initial conditions. So it can move above the barrier if you give sufficient initial condition energy, sufficient energy to the initial conditions, or it can be confined in a narrower place or part of the axis if the initial condition is below the barrier. Okay, and there is no way to escape this region under this conserved energy kind of dynamics that I'm showing here. Now, what happens if I add friction and noise, if I couple my system to a bath? Well, it can be easily argued and showed that what the particle will do, imagine that you initialize it within this well, is that after a certain time, which is rather long, is this Arrhenius time, the particle will be able to escape the initial well and go over the barrier and visit the other one, and then it will go back and forth over sufficiently long times, longer than this, from one well to the other. And in the end, if you wish, if you want to average and over all those long times, what you will, sufficiently long times that allow for jumping over the barrier, the average of the particle will be in the middle. Will be, if you wish, a position that corresponds to the top of the barrier, because it will be symmetric with respect to spending as much time on one well as in the other one. Okay? But if you don't give enough time, if you look at the evolution after initial conditions here, let's say, over times which are shorter than this Arrhenius time, the motion will be confined, jerky but confined within this well, because you don't have time to go over the barrier to activate the dynamics in this Arrhenius form. Now, what is the scaling of this, or what is the dependence of this Arrhenius time with parameters or characteristics of the potential? Well, there is some microscopic timescale here that it's not very important, but what is important is this exponential dependence on beta, once again, and the height of the barrier. That can be, this can be shown in different ways, as I said. So if the height of the barrier is very tall, very high, well, TA grows very fast because it grows exponentially with this height of the barrier. And this will come back later in more complicated situations. This is why I want to recall it here. Yeah. Fine. Okay. Don't hesitate and interrupt me and ask me questions. So just to give you an example of how the motion goes on in these cases, imagine that here I just plot some 5 trajectories, let's say. I starting, say, look at the red one, for example. I initialize it in the well on the right, so R is positive, and then, okay, it spends some time in this well, then it goes down, it spends a lot of time in the other one, goes back and forth and so on. And you can see that the times that it spends in the well is, well, very long, as it's here, and then when it manages to go over the barrier, then it does it very quickly. So this ramp here is very short, while this is very, very long, and I have somehow cut here my simulation. This 0 is not really 0. There was a long interval here where the trajectory stayed, say, of the same order or similarly to this length in the initial well.
So just like you had in the 1D case with, the relaxation time to get to equilibrium. So in the double well case, can you get a statement about, converging to the Gibbs measure on just one of the wells, as long as
exactly. So if you can if you do look at, for example, the
as long as the relaxation time is like less than the time
of the Arrhenius, then you can have restricted thermalization within the well where you are, and the relevant timescale here will have to do with how to say it, the curvature. That's right. Thank you. The curvature of the well, while this other time has to do with the height of the barrier. So it's a completely different thing. So if you look at times which are over this TA, then again you have full thermalization, so now over the two wells, and as I was saying before, and the distribution takes the usual Gibbs-Boltzmann form. Okay, so now I talked about equilibration, but now let me talk about dynamics under equilibrium conditions. So imagine that my system has arrived at reaching all these timescales as long as necessary. The distribution function of the position and the momentum is represented by a Gibbs-Boltzmann distribution, but now I want to compute time-delayed, for example, correlations. So the first statement about looking at just momenta or position, let's say, at a given time, the fact that the distribution arrives at Gibbs-Boltzmann, what it means is that these quantities cannot depend on time. They should be time independent, and they should be equal to the value that you would get just taking the average with the Gibbs-Boltzmann distribution. But now you can also compute time-delayed correlation functions. So you take your initial time in this measurement to be longer than the equilibration time, and then you take another time which is still longer than the previous one, and as many as you want, and you construct an n-time correlation function, for example. What can be proven is that under equilibrium conditions of Gibbs-Boltzmann kind, this correlation has to be stationary. And stationary means that it has to be time translational invariant. So if I add the same constant, delta, to all the times, then the result cannot depend on delta. In particular, the simplest case, and the one that will appear later, is the two-time correlation function, that it can, under these conditions, only be a function of the time difference between the two, of the difference between the two. So this is the stationary property. Now, the stationary property is not sufficient to prove that your system is in equilibrium, so of Gibbs-Boltzmann kind. So what I mean by this is that you can have, in different situations, steady states, where your dynamics satisfies for all correlation functions this property, but still the probability distribution that you are sampling in this way is not of Gibbs-Boltzmann kind. Gibbs-Boltzmann is more than that. So, for example, here there's no mentioning of beta, of the inverse temperature in the distribution function. So there are other properties that know about this beta and know about this exponential form in terms of beta of Gibbs-Boltzmann, that go under the names of fluctuation dissipation theorems, and what they do is they quantify how much the system fluctuates on its own and how much it will fluctuate under external perturbations that you will do on them. So, for example, the simplest fluctuation dissipation theorem is one that links two-time correlation functions to linear response functions. So this is the response that your particle position, in my example, will have to kicks that you will do to it. So, for example, a force with which you will pull from it, let's say, over a time interval that goes from tw to t. So imagine that you take with your particle, you push it with some force, and constant and very small, and then you take the limit of this force going to 0, you measure in this way the linear response, how much the position of the particle has changed due to the application of the force. So this is the fluctuation that you have induced with your force, and you compare it to the correlation functions, and independently of what's the problem, what is the energy potential, what is the potential that you're using, there should be this linear relation between correlation functions and linear response functions with this prefactor of kBt to the -1, that it's a property of only the Gibbs-Boltzmann distribution. So this tells you more than this. Okay? Both are necessary. This is not sufficient, but okay, this is telling you more. It's a better check of having thermal equilibration at a Gibbs bolt. These properties can be proven in different ways. I will not do it, but it's just mentioning. Okay, but now what about having out of equilibrium dynamics in these simple cases? You can have them. The one way to do it is to switch your potential off. So you make your potential flat. If you wish, you take it to 0. And in that case, what you can check is that the energy converges to the only contribution that you have to the energy, which is the kinetic one, as in Gibbs-Boltzmann, or as in Maxwell, if you wish, the kinetic part of it, but the position does not. And the position does not because there is no confining potential. There is nothing to put in the h in the e to the minus beta h from the potential. Or in other words, you don't have a normalizable distribution function to characterize the position of the behavior of the position. And there is different ways to see that. The simplest one is to see that the correlation function between the position does not approach a stationary limit in this case. It will go in the very long time run to a mean between the two times. And this is not stationary. This is not a function of t minus t prime. And you're breaking stationarity, and you also break FDT in this case, but I will not show it here. Okay, so basically what's going on is that you can approach a Maxwell distribution for the momenta, but you cannot approach one similar one for the positions, because you don't have a potential to bound the motion of the particle. So you have separation of variables here, two variables, phase space variables, momenta and coordinate, that behave very differently, and the reason is because there is no potential to confine the position. So this is the summary of the first part of what I have said. So under an environment which is itself in equilibrium, a confining potential, in the example I'm giving, finite barriers, you have equilibration of both P and R. You have exponential approach to equilibrium. Tau can be different, but okay, there is a tau. And Arrhenius activation over finite barriers, as I said before. And for the flat potential, you don't have equilibration either of P. You have equilibration of P, but not of R. Now, let me talk about coupling to different baths, because this will become, again, important later on. The simplest choice was a wide bath with no memory, so friction was a local term in time. Now I'm putting a kernel in the friction term, so the velocity here appears multiplied by this function of t minus t prime, and integrated over the full time interval. And the noise is correlated, and is correlated with the same kernel which appears here, and this is again a property of the equilibration of the bath. This can be also proven. But the bath has a memory. Now, what changes? So what changes is, for example, the way in which equilibrium is approached. So a case that...
Just to clarify that.
Yes.
The statement is that if these two quantities are not related to sigma b's, then it won't approach the
Indeed. If they were not, I will say it later. So if they are not related in this very special manner, so you imagine that this one is different from that one, or the coefficient is something else, then you don't show that, or the system doesn't approach equilibrium. But let me remain in the case of approaching equilibrium. So a case that can be worked out, all the calculations, is one in which you make the choice of having a kernel which is has a potential form, a potential decay with some gamma here. So this case can be solved again for the harmonic potential, and in the long time limits, what you will find is some function. Okay, it doesn't matter so much which is the function, but the way in which this function depends on times is through a power law, and the power alpha appears here. So this is not one. It depends on the form in which the kernel decays at long times. Only for alpha equals 1, which is corresponding to the ohmic bath, you will have an exponential relaxation. Otherwise, you have power law relaxations. Basically, these things at long times go like power laws. Okay, so you can change the way in which you approach equilibrium by choosing different kernels here, always respecting this relation that they are the same, as Daniel was pointing out. Now, you can play with baths now. I'm introducing this bath with a kernel. Now I'm going to introduce a complex bath. There will be a reason for that, you will see later, but just imagine now that I take the same oscillator and I coupled it to two baths. One is the white bath, and it's at temperature T, so the relation between this kernel and this kernel for that bath is just a delta function. It's a white bath, so the sigma b is delta, and there is a prefactor T here. And then I will take another bath, which I will make, for example, correlated with some function that I like to choose, but it's at another temperature. So now if I'm coupling my system to two baths which evolve at different time scales, they are different time dependencies, and have different temperatures, what will happen is that the system will not be able to equilibrate because it doesn't really know where to equilibrate to. And if I measure, for example, this deviation from the linear relation between the linear response and the correlation function, that in equilibrium should be a straight line, as I mentioned before, what I observe is that for this oscillator, which was a simple potential, there is a breaking line form for this relation. So it's linear by pieces. So there is a piece in which it follows the fast bath, the white one, and there is another piece in which it follows the slow bath, the one that I chose to have some power law correlations in time, and that it's a different temperature. And if I look at the slope of these relations, which is the one that in FDT corresponds to the temperature of the bath, what I see is that the first one follows the temperature of the fast bath, and the second one follows the temperature of the slow bath. So what have I done here? I have induced, by coupling my system to a complex bath with well-chosen characteristics, two timescales in the motion of my oscillator. And these two timescales are related to different temperatures, the ones that the baths are introducing into the system. Okay? When I said well-chosen bath, of course, if the timescales of the bath are not well separated, as I'm choosing in this case, then this construction will take a sort of ugly form where I could have some curved form over here. I don't separate the timescales of the motion of the oscillator well, but here I do. And basically what I'm trying to say here is that you have to imagine that your particle is moving fast with the characteristics of the temperature of the fast bath, but it's also moving slowly. This fast motion at the same time has a slow motion that it's following the temperature of the slow bath. So it's simple to, I didn't put a drawing, but you have to imagine something that's oscillating fast and also oscillating slowly. And these are the two timescales that appear here. Again, this is very easy to do artificially or not so artificially by coupling this very simple oscillator to two baths with different scales and temperatures. Okay, so what are the conclusions of what I have just said? Even the long-term dynamics may depend on the microscopic dynamics in the sense of the characteristics of the bath. This is what I mean by microscopic here. The approach to equilibrium can be non-exponential, so the case dictated by the noise correlations. This is in general has to be taken seriously because sometimes people say as you have to have exponential relaxation to go to equilibrium, but you know it's not necessarily true. It depends on the characteristics of the bath in this case. And the comparison between correlations and linear responses, these FDT kind of plots, gives more detailed information in respect to approaching or not approaching equilibrium, because as soon as you have something like this with this broken form or something like that, you are sure that you're not in equilibrium over the full time scales of the evolution of your system. Then, okay, again, simple problems. Imagine that instead of having a simple oscillator, yes? No, I mean, I don't know. But what we certainly can do is something, what we did in the past, was to think in terms of the slow motion as creating a field, so like on the fast motion, and separating the scales in this way. This we have done, but in thinking in terms of changing the temperature, I don't know. Okay. So now to try to complicate the things a little bit further, imagine that you still have a one-dimensional space, like here, but then you have a random potential. Okay? So these are two pictures that I took from this paper with potentials with different characteristics. So the sort of things that Ian has studied very much in the past, also with Pierre. So potentials that are correlated over long lengths, or longer lengths here than there. You can choose the characteristics of your random potential and then look at the motion of a particle in such random potentials. And people have studied this in a lot of detail. And these kind of problems that have been studied, as I said, in many, many details, and they're very nice long review articles describing what's going on, depending on the potentials and so on, have motivated models that in our community are called trap models. So models where you simplify this kind of potential and you propose that there are wells that would be the minima in this potential, which have some characteristics. So characteristics meaning the distribution of the depths of those wells. And in this, for example, and in this one-dimensional picture, okay, you have the wells like this, but then you can say, well, I can only jump to my nearest neighbor, or I can jump far away. You can play with these parameters, and these make different models of this kind. Of you can decorate the bottom of the wells with other little wells, again motivated by ideas from spin glasses or not. And it's okay. So there's a lot of family of models of this kind that have been proposed to describe now the motion of or the dynamics of complex systems, where instead of interpreting this as being a real one-dimensional space, you interpret it as being phase space. Or the space of configurations, if you wish. And then it shouldn't be any longer one-dimensional. You have to think that there are any dimensions below. And okay, there have been a lot of studies in the context of these trap models in relation with these other systems. I will not mention a lot about them, but I just wanted to mention them here because they have been really motivated by the study of diffusion in random media in finite dimensional spaces. Okay, so this ends the first part of my presentation, which is just about, dynamics in real spaces and in simple potentials. Now, let me go one step further and think in terms of what I think is the simplest free energy landscape, one that corresponds to problems with many variables and now in large dimensions. So the problem that I have in mind is one which is very well known by physicists, but perhaps not so much so by computer scientists. So it's the model or the system that undergoes a paramagnetic ferromagnetic transition. So it's a problem in which you have two phases. In one, you have spins that just are disordered. They point in up and down directions, say Ising spins, binary variables. And that if you look at the configuration of a system in 2D, so it's a plane, black and white are up and down. At very high temperature, the system is disordered. You don't see any pattern of spins pointing in the same direction locally. You see something like that. Below a certain transition in the temperature of the bath with which your system is coupled, what you will see is that the spins tend to order in one of the two directions. So, for example, in this picture, white. And there are some thermal fluctuations, some wrong spins that point in the opposite direction, but there are not so many, and they are somehow isolated in the configurations. So this is a typical configuration of high temperature. This is one of low temperature, and people have asked, how to describe this phase transition in simple terms. And what you have to do is to identify another parameter, a simple quantity that distinguishes between this and that, and some free energy function of this other parameter that will tell you when you go from here to there. So this is the Ginzburg-Landau approach that effectively identifies the local order parameter, the effective weight of that order parameter, the free energy function. Yes?
Are the words well and bad synonyms?
Well and?
Bad.
No. Well is, in the potentials before, it was the form of the potential energy that I have. So when it has a dip like that, I call it a well. The bath is the environment with which your system is in contact. It's not isolated from the rest of the world. It has some connection with the rest of the world. And what this means is that it can exchange energy, basically, with the rest of the world. And the rest of the world is enormous with respect to your system, so typically you will always be given energy from your system. So this is why there is this relaxation. You're welcome. Is there other questions? Okay, so the model, the cost function or the Hamiltonian that characterizes this problem is one of this kind, two-body interactions over nearest neighbors on the lattice. There is a sense of locality here. Coupling constants, which are all equal to some constant value, and you see that you minimize this cost function if J is positive, if you put your spins parallel, but you can put them parallel up or parallel down. So there is symmetry between these two configurations of up and down. Now, working with this spin Hamiltonian is difficult, so what Ginzburg-Landau did is that they identified that locally the system tends to try to order. It looks, one spin looks at its neighbors. It says, I want to be like my neighbors. So locally, this sum over boxes, let's say, of the spins that I'm calling here phi, it will become a field of the position. This is a natural thing to consider to be what's going to characterize the local order. And again, a natural function of this, or functional of this local parameter, derived or argued how to derive by Ginzburg-Landau, takes this form. So there is a term here that penalizes the phi taking different values over nearest positions in space. So this is the gradient here. So this forces the phi to be the same over distance. And this is like a potential density, potential energy density that it's proposed to take this kind of form. So there is a form that describes what is expected to happen at high. There are these lines here. I don't know. Anyway, so there is this form of this potential energy density with a single minimum at 0, which is the one that characterizes the high temperature situation where the system wants to have a phi equal to 0, no order. And there is this double well structure below the critical temperature that has these two minima, which are the same heights. They are degenerate and correspond to order down, order up. But this is a function of the local order parameter. And the barrier in this local energy density function is order 1. Okay, so phi is order 1, everything is order 1 here. And you go from one to the other by choosing the sign of mu. Okay, so now I said already that the elastic term tends to tell you that all the phi should be the same. So let's imagine that it fixes really phi to be independent of distance, independent of position. Sorry. So then you can go from the free energy functional that I showed before to a free energy density. Now I divide it by L to the D. And what remains is the integral over space of this potential energy density, but now this doesn't depend on R, so I take it out, so it's a V of phi. Okay, so this is little f is order 1 again. And the form that it has is the same as before, something like that. And now what you can do is an argument like saddle point argument, or okay, there are different names to. Okay, you usually use. There's another name which is fashionable now, which I don't remember. Anyway, so you look at the configuration that minimizes this kind of free energy density here, and what you find is that above the critical temperature is 0, below the critical temperature you have the two possibilities, positive and negative. Okay, and this saddle point that corresponds to the minima here is such that V prime is equal to 0. This is extreme condition, and V second positive to have the minima. The barrier, delta F, here again is order 1, but the barrier in the free energy functional, the one that is extensive, is not order 1. It will diverge with L. This is order 1 because I divided by the volume. Okay, now this is what is known about the static properties, the equilibrium properties of the system. Now I want to do dynamics. So I want to say I start from these kind of initial conditions. I set my temperature of the bath to be below the critical temperature. What does the system do? How does it reach this equilibrium situation where everything orders in the same direction? And the way to do that is to extend the Ginzburg-Landau equilibrium approach and make it dynamic. So what you do is you propose a Langevin-like equation for the evolution of the local order parameter that now also depends on time. And you have a term that you propose, like the deterministic force, is the gradient over this free energy functional. And then you have a noise. I have dropped inertia because it's a good approximation for these problems. And you see the relation between these two is the one that may allow, I didn't write the correlations of the noise, sorry, forget about this nabla here, it was an extension. So the correlations of the noise are delta correlated with a good 2 kBt factor in front of that. So this kind of Langevin functional equation allows for the approach to equilibrium, because the bath is in equilibrium. But how it does it is a complex phenomenon, and you will see how it is going. So basically, if I want to think about this process now in looking at this free energy function density that I showed before, the little f as a function of phi, I start from an initial condition with phi equal to 0 because the system is disordered, so phi is equal to 0. So I start from the top of the barrier. And naively, one would say that the process of ordering, the spontaneous symmetry breaking of choosing up or down globally, corresponds to quickly rolling through this slope here, say from the top of the barrier to the minimum on the left. That would correspond to, after this quench from high temperature to some temperature here in this plot, quickly, ordering. But this is not what's going on. What's going on is that there is a slow process, look at these plots here, where the system is locally, progressively ordering, but not globally. Global is still disordered. And this is time, and it takes very, very long. Actually, it takes times that diverge with the system size to order fully the sample. So this idea that you will jump over here or you will jump over there globally is not true. What's going on is that if I now look at this local potential energy density, in some places the system is going here, in some other places it's going there, locally. In some places it's going up, if you wish, in some other places it's going down. But globally it's still on top of the barrier. Globally phi is 0. So in the L going to infinity limit, for times which are finite with respect to L, the global or average order parameter vanishes. And the representative point in this kind of picture is on top of the barrier, and it remains over there for all these times which are finite with respect to L. Actually, one can show in this problem that you need times that go like L to some power to reach equilibrium in one of the wells, so the restricted one you were asking about. So that one goes like L to some power, while, I think I wrote it somewhere, I don't know where, while the one to go above the barrier will be exponential on a function of L, which is the height of the free energy functional, the one which is not normalized by L, I mean the global one, the total one. So now how do I interpret what's going on in terms of this double well picture for the free energy density as a function of phi? I'm on the top of the barrier, okay? But this is a one-dimensional picture. So in a one-dimensional picture, if I was thinking in terms of motion of a jerky motion of a particle, thinking that phi is like the position of a particle, a tiny noise will make me fall on one side or on the other. But I'm not actually on a one-dimensional system. I have LD minus 1 other directions, which are not plotted here, that characterize the configurational space of this problem, that are hidden. I'm not writing them. I'm not drawing them. So over this one-dimensional direction, the system is on top of the barrier. Over all the other directions, basically the potential or the free energy landscape is flat, and it can be changing a lot. It is changing a lot because there's all this motion or these changes in configurations which are going on. But on this direction, it's there. So the idea that it will fall because of the noise and so on and so forth, is a misleading one, because one is, in these kind of plots, neglecting the fact that there are all these other directions, and that actually the motion is going on a high-dimensional space, which is the configurational space. Okay, so these scales that are involved is a power law in L to approach order, and an exponential in delta F, as I said already, like an Arrhenius one, to jump over the barriers and do global reverses. But those are so long time scales that okay, they're just not very relevant. And this would be the sketch of what the phi would be doing if we had enough long times to make the system reverse. But okay, these scales are already very long, and these are even much longer. Okay, something else I want to say is that in these cases, it's very easy to pin or to drive or to push the system in the direction of one of the two others, because the only thing one has to do is to add to the Hamiltonian a field, an applied field, uniform, say positive, and then you impose that phi, that S, and also phi will rapidly go to the equilibrium state that is chosen by the field. Notice that this is a perturbation that you applied to the Hamiltonian, which is order n. So it's the same order as the original Hamiltonian that you had in terms of number of variables in the problem. So it's a volume-like perturbation that you're doing. So this is good to take the system to equilibrium. So in this problem it's easy because you know which are the other states that the system wants to go to, but in other problems, of course, it's not so easy to identify which would be these pinning fields. You are interested in flat directions in this context. Okay, there's this paper that I don't have a lot of time to discuss. Now, concerning the effects of the bath, everything I said was dealing with a white bath. Now, what happens if one puts a color bath? Again, with a color bath, what will change is the time scales in the problem. Okay, this is a little bit technical, but just to say that there is a region of parameters where, for example, the power laws that control the approach to equilibrium, in this case it's at the critical point that the calculation was done, depends on alpha. So you can also choose, if you wish, the velocity with which the system evolves by choosing the bath, and this has some implications in the quantum world, but okay, let's forget about it. Okay, so this part concerned non-frustrated collective relaxation, the case of ferromagnetism. We already have a slow non-exponential relaxation. There's time scales that scale with the system size, non-trivial collective effects and competition between these only two equilibrium states that the system wants to go to. From the point of view of landscapes, the importance of flat directions along these hidden longitudinal, I like to call them directions. There is effect of bath correlations that can be introduced, and there will be more on effective Langevin equations with memory later. Yes?
So here, you are starting from a random initial configuration. Do you know if you can tell which well you're likely to fall into given the initial configuration, or for a given one it's equally likely?
When the system is sufficiently large, no. I mean, it's which of the two...
Most initial configurations don't tell you any information.
No, not really, no, because it's with probability half, you have as many up and down spins, and then you have the noise that will change this, which are the ones which are up and down, and very quickly. So it's
a correction to the half that you can say that there's sort of information in there.
Indeed. Okay. So if the system is small, then you will have a correction to the half, and then, okay, you will have a bias in the initial condition that may lead the system to one of the two equilibrium states. But in the infinite size limit
the
with...
geometric things of like the clusters don't...
Okay, then we can discuss it if you wish, because there are very nice results concerning the geometric organization, but those go a little bit beyond what I want to say today. But if you're interested, I can tell you more about that. Yes, there are some hidden issues about the geometry that are interesting and nice. But
one, of course, can pose boundary conditions.
Okay, yeah, if you want, it's very easy in this problem to choose one of the two, because either you unbias the initial condition a little bit and then, okay, then you go to the one that you have chosen. You can impose boundary initial conditions, as Jan was saying. This is very easy. This problem is very easy. But if you don't unbias it in any way, then you have all this competition that goes on forever. So other questions about this? Okay, so now let me go to the interesting case. Yeah, I think I have 20 minutes is fine. So let me start by defining the modes. Many of them you have already seen. Then I will go to show you which are the equations that one can use to study the dynamics of those models. There are two versions that can be used, and both are interesting and useful for different purposes. I will focus all the results on pure p-spin models and SK-like models, and then Federico later will talk about another case, which is a little bit more complicated and has aspects of the two. This is kind of introduction, if you wish, to the problem, and then I will talk about results. So how separation of timescales appear naturally in these problems, how breaking of stationarity appears, how breaking of FDT appears, how this can be interpreted in terms of effective temperatures and partial thermalizations in the problems, in the dynamics, how the results can be interpreted from the landscape point of view, and the effect of non-potential forces, if I have time, because this may be of interest for you. Okay, so on the left of the slide, there are realistic physical problem potentials, either of particles in interaction or of spins in interactions in spin glass systems. Of course, these are difficult to study. We don't study. We very quickly jump to the right side of the slide. And the right side of the slide defines p-spin models that you have already seen, fully connected ones. This is a sketch for two-body interactions, and the potentials will have terms of this kind with p spins that interact via interactions strengths, which are taken from a probability distribution, normal probability distribution, as we have already seen. So they are quench random variables, quench disorder, typically Gaussian, zero mean, and variance 1, normalized to have a good thermodynamic limit. Okay, now I want to do dynamics on these problems. So the idea is to first go to continuous variables. Don't work with easing, because easing is complicated. So you can go to continuous variables either by working on the sphere, as you all know, or by imposing a local potential, double well-like potential on each variable, on each spin, that favors plus or minus 1. I will just do spherical, so forget about the other option, but just to say that easing can be treated in this approximate way as well. Now, the Langevin lag dynamics that one proposes, typically working on the Overdamped limit because it's simpler and also enough. There is a friction term, there is a noise, there is a force. What's the force? The variation of the potential with respect to the spin Si. For the potential, then you have a form of the one that I said before. And if you have a potential, these terms or this factor is symmetric, fully symmetric with respect to exchange of all the indices here by pairs. So these as well. Okay, so the J's are symmetric with respect to all the exchanges of the indices. And later I will mention other cases. Or later even below. So if you construct the force in this way as the variation of V, then all the J's by construction are symmetric with respect to exchanges. Now you can also add the non-potential forces at the level of the force. Instead of defining it like this, defining it as this. So it's the same as you would get by taking the variation of V with respect to S, only that now I don't have a sum over the Si, over the I1, this first index. So the only symmetry I have to impose is between the exchanges of the indices that come later. So I could change, I could choose the J's to be fully symmetric with respect to all the indices after the first one, and, for example, asymmetric with respect to exchanges of the first one with the other ones. So this makes this force not derivable from a potential, and this is a non-potential force that will inject energy into the system, and perhaps it will help jump over barriers. Because remember that I only talked about jumping over barriers via thermal activation. That those were like kicks that the bath was giving on the particle to make it go over the barrier. This force here may also have this effect of making the energy go up, help the system go over barriers, and then fall somewhere else. So, yes, please.
If there is no potential, how can you speak about barriers?
Okay, so you can speak about the barriers generated by the symmetric part of these J's. You see the J's? When I say asymmetric, I don't mean antisymmetric. So there is to the asymmetric, there is a symmetric and an antisymmetric contribution. So the fully symmetric contribution, you can think that it generates a potential landscape. And the antisymmetric part of the J's is making the system move around, jump, turn, do a different kind of dynamics. So this is the what I have in mind, that this is the generation of the underlying potential is made by this fully symmetric part. So, yeah, thank you for the question. So other questions about?
Choose the indices where the J's are asymmetric, right? Always the first index of...
Yeah, because you see here, necessarily the indices going from 2 to p are symmetric because I have all the factors here, I have all the factors there. Oh, this is 2, sorry. Yeah. This is a mistake. This is a typo. So it starts from the number 2. This is a typo. Yeah. It's I. Yes, indeed. Yeah, this is I. Yeah, sorry for that. Yeah. Okay, so there is one which is different from the other ones because it doesn't appear in the sum. Basically, this is the reason. Okay, these have been proposed in the context of neural networks in the past, these kind of forces, and also rheology. So there is also a physical, if you wish, motivation to look at these kind of forces. Okay, now what about the initial conditions? If I want to mimic quenches from disorder phases into some low temperature situation, I can take the initial conditions from a probability distribution, say a Gaussian centered in 0 with some variance, but basically average of SI being 0 and no bias. Or I can choose correlation functions that know about the symmetric part of the interaction strengths. For example, I can choose the initial conditions sampled from the Gibbs-Boltzmann distribution at some initial temperature beta initial. And these know about the J, the symmetric part of the J, because the symmetric part of the J is within the Hamiltonian, right? So these initial conditions are correlated with the random potential, and I could play with where I choose them, and you will see how later on. Now there was, in the Ian's talk and some other talks, the notation was such that the correlations between the potential was defined via function f, which depends only on the correlation between the two configurations, the overlaps between the two configurations involved here, and this is the notation I will use also later. And the normalization, again, is such that n going to infinity is a good thermodynamic limit. Also, Marc Mézard used this definition in his talk. Now, in the n going to infinity limits, these microscopic dynamics actually can be described only in terms of two-point correlation functions and linear response functions. I guess that Amir may talk about this in his talk afterwards. But without proof, let you believe me that everything can boil down for these models into integral differential equations that I will flash later that apply on this self-correlation between two times, linear response integrated over time, defined in this way. And if I have special correlation functions, the correlation with the initial condition will also play a different role. So the equations look like this. Amir will give a talk about the mathematical proof of them. They are differential operators on the left. They are integrals on the right. They are convolutions or integrations over C's, D's, C's and R's that appear combined with the sigma and D. What are sigma and D? They are kernels that depend on the correlation of the potential, but they are known. I mean, once you know the F, you know the D as a function of C, and you also know the C, the sigma as a function of C and R. So these are closed integral differential equations. There is an extra equation that fixes the Lagrange multiplier for the spherical problem. I'm not writing it. And these are how the equations look like for random initial conditions. As I said, the C and the D are known. If I write them compactly as a function of force of C and R, what I notice is that for these problems, which are potential, they have a simple relation. There is a simple relation between the two. So the sigma is D prime times R. If I break this relation between sigma and D, I'm considering non-potential forces. Okay, so this relation ensures that the forces that I was using derived from a potential. So this is what I'm saying here. So non-potential forces lead to sigma and d that are not related in this way. And in a sense, this is an explicit violation of FDT within the system, but okay, then let's not put it in these terms. In any case, also for non-potential forces, the differential equations look like this, and this is what you were asking me the other day. So yeah, one can write equations, but now there is no simple relation between sigma. Okay, now if I impose initial conditions of a special kind, the equations look a little bit more complicated. There are terms that depend on the initial conditions. I don't want to go into the details, but these have been worked out by these people in the past. And you can play with the parameters, which are now the initial temperature of the initial condition, and the working temperature, which is here. But apart from that, okay, you have one more equation, but again, you can deal with those. There is another way of dealing with this problem, which is dealing with an effective, how did I write it? Yes, with an effective Langevin equation for a single spin or a single variable. It looks like this. So compared to the equation that couples all the spins, here you don't have different indices I. You see I is always the same, so there is a single spin. But by integrating away, or getting rid of all the other spins in a way which is similar to what's done in mode coupling or in dynamic mean field theory, what appears is a kernel which is time delayed here. So it's like an effective friction imposed by the system itself on the spin that you have chosen, that you have selected, a self-generated friction, as well as a self-generated noise term, another one, an additional one, which is correlated in a non-trivial way, and with the d, which is the d related to the sigma in the way that I mentioned before. So in this presentation, the problem became the one of a Langevin equation of a single variable, but with two noises. There is the white noise, the original one, in orange here, and then is the self-generated bath, which is the one that the system is doing on this selected variable, or it's applying on the selected variable. Okay, so this presentation also has some merits. It can be used in different ways, because now I can recall what I said about two baths for a single variable in a simple potential, and you see that okay, there are these non-trivial baths appearing there. Okay, now what do we know about free energy landscapes? We know a lot. I'm not going to review everything, but let me just review it in this old and ugly plot that I took from an old paper, which is how these free energy landscapes look like for two representative models. So p-spin, pure 1p spin model, and scale-like models. So for the p-spin model, what we have is that there start being minima in this free energy landscape and saddles of all kinds, rather high up in free energy density. So this is free energy density that I'm plotting. Sorry, this is total free energy. This is, I didn't put the F. This is free energy order n that I'm putting here. So high up meaning order n up with respect to the equilibrium, which is somewhere here, you start having a structure. In particular, there is a limit, there is a region that can be characterized quite well, that is called the threshold, that is flat, and it's very large. So there is a lot of configurations that belong to this flat threshold level that is separated by order n from equilibrium, which is here. And in between, there are lots of metastable states with a lot of barriers that scale, we think, like n, and you will see one of the evidences for that claim later. And, and below, there is equilibrium. So there is this kind of gap, order n, between this threshold, lots of metastable states, and then the equilibrium down there. For scale-like models, this threshold goes down. I mean, there's no threshold, and there is no, this is like pushed down. I will make this sketch later on. Now, what happens if I solve those equations? Okay, I solve those equations, both for scale-like or p-spin-like models. What I notice is that the correlation function has a separation of time scales. So what I mean by that is that now I look at, say, at t prime fixed and look at how it behaves as a function of t. I will be able to characterize it as a sum of two terms. One is fast, this one, and one is slow, that one. One is stationary, depends on t minus t prime only. The other one doesn't depend on t minus t prime only, depends on both times. And it's this curly C that I have here. And one interpretation of what's going on, I will show you the plots later, concretely for the correlations, but one interpretation of what's going on is a bit like what I was saying about the system coupled to two baths, once again. I have a fast motion that I can interpret as oscillations in some nice well, harmonic well, let's say, that I'm calling transverse motion. And there is characterized by this contribution, and there is another contribution to the dynamics that is telling me how this drifts along flat directions, and these flat directions are the ones on the threshold, because you will see that the system converges to the threshold after a quench from infinite temperature, not to equilibrium. On time scales that don't scale with n and that don't allow for thermal activation over barriers. Okay, so I have this combined motion, like I'm doing like this, but at the same time I'm moving like that. And this moving is very fast, and the other one is very slow. Okay, so the correlations look like this. Each curve is for a different t prime, and the decay is different for different t primes, and this is the non-stationary part of the behavior of the correlation. But this first rapid decay towards a plateau, which is basically related to the width of the well, of the oscillator well I'm thinking about, this is stationary, depends on t minus t prime, but then it goes down in a way that becomes slower as longer is the t prime. Why so? Because I have to think that my threshold is not completely flat, it's a little bit tilted, let's say, and it becomes flatter and flatter as I go on in time. So my dynamics becomes slower and slower as I go in time because I have smaller slope. This separation of timescales, I see it in the correlation, I also see it in the response. This is the integrated response, it's turned round with respect to the other one if you wish. So these are sketches of separation of timescales in the out of equilibrium relaxation. Out of equilibrium already I see because of the waiting time dependence and the non-stationarity. Now, if one observes from, say, for example, numerical solution of those equations, this separation of timescales, you can plug an ansatz like this into the equations, work a little bit, quite a bit, and you can solve the equations. And from solving the equations, there are a certain number of features that can be derived, and other ones that cannot. But at least one can find that a solution with this separation of timescales is self-consistently accepted, let's say, by the equations solved with these ansatz. And it's moreover realized numerically, so it's okay. One is happy with this solution. One can characterize these correlations more or less in detail, but one thing that I want to mention, not discuss, but at least mention, is that in this slow part of the decay, one observes that the variation of the correlation is much smaller than the correlation itself. This induces time representation invariance into the equations. This has some interest, especially in characterizing fluctuations, but I will not have time to say. So let me summarize what's happening then from a free energy perspective. So I'm quenching from very high temperature, so initial conditions at very high temperature, going down to low temperatures. Low temperatures below some dynamic temperature, which I'm not, which is here, which is, okay, some dynamic critical temperature. Below this dynamical critical temperature, my system is not able to equilibrate anymore in times which are finite with respect to system size. What it does is that, for example, if I plot the potential energy, what it will do is that it will approach this threshold level of the potential energy itself, and it will remain there. So, for example, if I do the calculation of the limit of t going to infinity of energy density divided by n, where I took n to infinity first, I get this E threshold. And this E threshold is larger than E equilibrium, which is a little bit below. But other one below, so it's, and this is our densities. This has been confirmed from dynamic tap approach derived by Giulio in the 2000s. And again, from the point of view of the landscape, this is a picture, this is a sketch that tells you how I could interpret what's going on with these quenches. So if I were to quench above the, okay, so let's just look at this one. So this is the kind of situation I have in mind. So I quenched to a temperature below the dynamical critical temperature where I have a threshold. I have a threshold, my dynamics converges to these white zones, let's say, which are like a sea level. And the other ones are mountains I cannot go over. And my system is like a ship which is sailing and moving around these directions. These directions are flat, the level of the sea is flat, and, but it has a lot of space to go and look at, and so on. And you have transverse motion, which would be doing like this across these channels, but then you have this other longitudinal flat motion along the channels. So this is the picture that we have in mind. Now, okay, let me do something else. So imagine that I choose initial conditions at levels of my free energy density or energy density, which would be below the threshold. So below the threshold, I have these barriers, right? Now I have minima. I know we have minima with n scaling barriers between them. So it would be like initializing the system in one of these lakes. I put the ship in a lake. The ship will move around the lake, but it will not be able to climb the mountain. So it will remain confined with these well-confining wells, with now barriers diverging within between them. And this can also be done, okay, this kind of, I have a lot of things to say that I will not be able to say. So for example, by initializing the states, the systems like that within wells, you will see that the correlation function does not decay to 0. It decays to the system, to the size of the well. A non-zero value here, and that's another thing. Okay, so let me choose what I want to say.
Can you
yes.
on energy density with which you start?
Sorry, with which you start?
You start with some. You start with random initial. Right?
Yeah, no, but I can condition.
Condition on energy with which you start.
Yes, yes.
So in principle, you can condition to start as low to.
Yeah, indeed. So these equations that included these extra terms with beta in within, by choosing this beta in, you choose the level of the energy with which you start, and you choose where you start below the threshold. You can do that. Yeah. It's not technically much more complicated. It's a bit more complicated, but it's not much more complicated. Okay, so you say I have 5 minutes. Okay.
Sure.
Huh?
Sure, yes.
Sure, yeah, they're very, very strict about that, right? Okay, so let me talk about FDTs, and then if I have time, I'll mention something about non-potential forces. So I showed already a picture like this when I talked about the oscillator coupled to two baths. Now, what happens in this problem, let alone couple just one single bath, but evolve in this non-equilibrium situation where it's approaching the threshold? The construction of this chi against C that in equilibrium would give a straight line with a single slope also gives two slopes. And it gives two slopes with a different slope. So from the second slope, the one which is not the temperature of the bath, one could say that one is obtaining a different temperature. Okay? So this, apart from saying it, there are ways to argue that this is true, that this slope is behaving as another temperature that the system is feeling. So the idea here is that, again, fast motion is controlled by the coupling to the bath, by the temperature to the bath, and it's what's going on here for the fast part of the decay of the correlation. And the slow motion is controlled by the interactions of the system itself, what's, it wants to do, and it self-organizes to be like feeling a bath at a different temperature. But this bath is self-generated, and this different temperature is chosen by the system itself. Okay, this is what I said. Now, as I said, one can play with coupling with different baths, and even for a P-spin model, introduce an extra scale here with a different temperature. So there is one slope, second slope, third slope, and this we did by coupling to another bath, colored and with a different temperature. So, just to insist upon the fact that these temperatures have a meaning as a temperature. They also have a microcanonical sort of meaning because they can also be obtained by looking at the variation of the complexity, so the volume occupied by the threshold with respect to the level of the free energy evaluated at the threshold. This is what I mean here. So this is like the microcanonical definition of temperature, where this is the entropy. But which entropy? The entropy of states which are at the level of the threshold. And this is a calculation that was done by Rémy Monasson in particular some years ago. And so you can do the static calculation, metastability, and then you do dynamic one, and you find that these are the same. So this gives support to the idea that this is at temperature. Okay, this I will do. So I talked about relaxation after a quench, separation of timescales, stationary and aging, FDT and violations, partial thermal equilibration, these two temperatures that appear naturally, approach to the threshold, flat level where marginal flat states are, and this can be confirmed by Hessian analysis of the free energy landscape if you wish. Now, everything is order 1 above the equilibrium energy density. If one wants to go below, what should one do? Either start below, as Ian was saying, by choosing particular initial conditions, or consider times that scale with n in a different way, I mean, that don't remain finite with respect to n. At the level of the dynamical calculation, we don't know how to do that. So this is open. It's very hard, but it's open. Now, just 2 words about SK model. SK model, this threshold doesn't exist, so this goes down. The barriers are probably with this exponent 1/3, as we were saying before, at least the ones that separate equilibrium states. But okay, there are no strict results about that. But definitely everybody believes that they are smaller than n, so this alpha should be smaller than 1. Now, what happens with the solution of the dynamic equations, it can also be worked out. It's a little bit more complicated. So, for example, the chi and C relations is not piecewise linear. There is a linear part which has to do with the dynamics dictated by the bath, and there is a curved part which has to do with the internal relaxation of the system itself. This is linked to the existence of a sequence of timescales. So there is no separation of timescales between 2 timescales, like in the P-spin model. But what you have to think is that there is a continuity of timescales beyond the one dictated by the thermal bath. This can be made formal by thinking about how correlations compare between themselves, picking times that are separated in different ways. And actually what it turns out to be is an temperature extension of ultrametricity. So it's like ultrametricity in time. If you take 3 correlation functions, they are related in this way, with T1 and T3, the ones which are further apart. As far as I know, there is no formal mathematical argument or proof of this, but in any case, it's what solves the dynamics of the problem.
But even from a physical point of view, I mean, here it's much shakier, because from what I remember from these papers is that you do perturbation in T minus T critical.
No, you don't need to do that, because you can do it, for example, in spherical models which are solvable.
In Ising models.
In Ising models, you do perturbation around T critical.
Also in the double well potentials. There is the quartic.
The quartic term, indeed.
So it's a double perturbation expansion.
Yeah, but you don't have to stick, to SK model. You can say I take a mixture of p spins, for example, that is like ultrametric, or I can take the random manifold in the manifold in a random potential, and there you don't have any perturbation to do, and there it's.
In SK really, even from a physics.
Yeah, but okay.
So usually it's an expansion around TC.
Yeah.
For SK rising spins, it's an expansion.
Which is is a problematic expansion, because in sort of renormalization group language, the fixed point controlling the low temperature phase is at 0 temperature.
Yeah, but I don't think it's important. I mean, you can say, okay, I define the model this way. Don't call it SK. Call it SK prime. And for that Hamiltonian, or for that effective.
No, I'm not saying I believe this conclusion.
Yes.
Yeah.
No.
Nice to have,
I guess that if a mathematical physicist would like to do something here, better do it in the spherical case first, right? Because there you don't have your problems.
And there's subtlety about dangerous irrelevant operators and stuff.
About, sorry?
About dangerous irrelevant operators. I mean, maybe it's okay, but
No, I don't think so. I mean, I have a well-defined problem, which is a spherical model with a fully connected hypergraph. So then, for SK, okay. For SK, you have these extra perturbations. But for a spherical model, it's the definition of the model, and then yeah.
Can you do I mean, even for SK, there is a
Yeah.
ansatz that you do close also.
Oh, it's true. Yes. Yeah, for the single particle, you mean? But he was also complaining about the soft potential for the single spin.
You can write the dynamical mean field also for the Ising. You have global
Yeah,
dynamics.
that's right.
of the noise.
Yeah.
But then, I don't know, can you plug in the ansatz in this?
Yeah.
As a
Yeah.
Yeah. Well, we discussed it actually in Paris a few weeks ago. So there is a paper.
Yeah. There is a hidden paper by Jorge and me that nobody read from published in an obscure Japanese paper. I can give you some conference. In Japan, no, not in Japanese, unfortunately. Anyway, yes. Okay, so this is, we can discuss it later. I mean, there's much to say. So there is this also, I want to mention this nice connection between the dynamic solution, yes, and the replica structure. Okay, so without spending a lot of time, because I don't have time, in a sense, time is playing the role of replica indices. And what you find, I mean, explicitly by doing the solution, the dynamic solution, and comparing to the static one, is that this inverse temperature, inverse effective temperature, which is here, is like, let me call it x of c to make it more similar, and you compare it to the x of Parisi, and you have the same functional form. And you can define probabilities of correlations as well, and do the same. So there is this, this connection that has been discussed again also by Mark in very nice papers that has been discussed up to a certain point, but I think that it's also would be nice to be deeper about it. Okay, so let me just, I don't have time, so let me see what I choose to say here. Let me show this one. So these are just, to conclude, an old idea of how you can use these non-potential forces to sample, I mean, to look around the trapping tap states in these p-spin models. So the idea is the following. So here I'm showing just energy as a function, energy density as a function of time. And what is going here is that I'm using these models with an asymmetry. So this relation is not holding. And what you see is that the evolution has periods of frozenness, so it's frozen. It's a very low temperature that I'm using. So the system is here confined in states. And then there is rapid motion. There is like chaotic motion when it got a kick from the non-potential force. It took it out of this confining region and it moves around. Now, if you look at the timescales here, you have timescales which are up to 10,000 and here 100,000, and the plots look the same. So there is some sort of cell similarity that nobody studied in detail, I think. So it's something that merits a little bit more attention, and that with a new interest in different problems that there is now, I think we are going to do it, and also Giulio and Chiara and other people are looking at these problems as well. So this I can jump. So let me state what I didn't show about finite n and non-potential forces. There is evidence for trapping below the threshold. There is possibility to test trapping ideas, better characterization of trapping times, perhaps barriers, I don't know. Chaotic periods, what's the system actually doing there, and maybe links to the results of Gérard on the trap-like dynamics at very low energies in p-spin models of Ising kind. So I will stop now, but just a second. Everything I showed, if you noticed, I'm sure you didn't notice, but I noticed when I prepared my slides, is before 2000. Was published until 2000 included, but there is almost nothing after 2000. So what happened next? I mean, I wanted to give a tutorial, so I had to talk about old stuff and established an old stuff, let's say. So actually, what happened after 2000 is that, in a sense, these kind of approaches were applied in different areas, no? So many different areas. So, for example, not very far away from what I'm saying, but different anyhow. So, for example, non-potential forces were used in rheological description of soft condensed matter. So this is, for example, the thesis of Ludovic Berthier that you all know was about that. We worked on descriptions of fluctuations that I didn't explain, glassy aspects of active matter. You can talk to Grzegorz there at the end of the lecture hall, who has been working on this more recently. There was also a line of quantum, so me in particular, I went quantum. So quantum dissipative problems, a lot of people were and still are working on this with these similar kind of models, but now adding quantum fluctuations. Quantum in isolation, which is quite fashionable now, discussed issues about integrability versus thermalization, and of course all the problems that are of interest to you and that are more recent still. There are some people in the audience who have been working on that. We had Lenka's talk the other day who showed similar equations with more detailed analysis, and also perhaps Daniel will talk about this in ecological context. Okay, thank you.
Can you go to previous?
This one?
Yes.
Yeah.
So, in this, was the ecological constant, but context. But basically, we have this studied fixed points of these dynamics and
yes.
their statistics, and now stability. We hope to finish it soon. Basically, we found that when you introduce non-potential forces, you immediately wipe out all stable, fully stable equilibria. There are no any, but those with finite number of, not finite proportion of unstable directions, they still exist. They may trap it for a long time, but they're not fully stable, so you eventually go out. So maybe it corroborates. We thought that maybe it corroborates with with your numerics.
We haven't studied the numerics in sufficient detail. I'm also doing here, but it's a bit tricky, no? Because how do you define the trap, the trapping time? Do you really get out of the trap? All these issues are very, very tricky. So
it's just simple observation.
Yes.
I had a question, mainly a curiosity one. So you mentioned that non-potential forces were used for neural nets.
Yes.
Could you just expand a bit?
Yeah, well, like I said, Nicolas probably will talk about this later. I don't know. But Nicolas Brunel. But the idea is that these synapses are not symmetric, right? So, that it's not the same interaction between neuron 1 and neuron 2 as with neuron 2 and neuron 1. So then a simple way to mimic this is by using these coupling strengths which are not symmetric. But then you cannot put it in the Hamiltonian, of course, because they disappear. But you can in the dynamic equations. So, yeah.
There's no further question.
Yeah.
Sorry.
So I don't know whether it's a question or maybe a comment also for scientists. So if I remember correctly, when you study active matter, when you have a system that actually is very slow with, let's say, normal conservative Langevin dynamics, when you do something which is, say, violate detail balance, then you can actually go to much higher density, right? For example, for spheres.
Yes, it's true.
Or lower energies, which means, I mean, in this are concrete example in which doing a dynamics that violate detail balance, you can reach configuration which are much better in terms of, let's say, cost function. So I don't know whether, in this case, the way to violate the detail balance is clear because it comes from, let's say, physics, but I don't know, maybe for sure this is something more
Something
general.
that we noticed, I didn't show this, but this is Daniel Stariolo, who's in Paris now, and he's working on this. For example, doing the non-symmetric dynamics for the p-spin, what you see is that on average the energy is higher because you are injecting energy into the sample, of course, with this force. But then you can reach certain traps that otherwise you wouldn't reach with just a relaxation that blocks somewhere else. So you spend a lot of time where you shouldn't in all these times. This, for example, here, in all these periods in which you are moving around, but then sometimes you are able to go to some rare situations. But then you have to find them, and they're not so easy. So.
Well, just to add to that, that's general. That's more general than in dynamics. So you can go to a target probability distribution, which would be the equilibrium distribution of an equilibrium dynamics. And it's known that if you can design a driven dynamics that takes you to the same probability distribution faster. And in a sense, you're not gradient descending. Well,
yes,
I don't know exactly the correct term. You're not gradient descending, but you're going round in circles. and you converge more quickly.
Right.
So this is known, and it's not mean field.
Yeah,
So it's
actually,
genetic.
I had in mind also simulation by Ludovic, in which he can really reach higher density, if I remember correctly.
Yeah, but there is a theory. There's a recent theory for this. Yeah.
But yeah, this has been studied also. This has been studied also in computers. I mean,
I
the
imagine.
example is the circle, right? If you do a circle and you do symmetric random walk versus asymmetric random walk, and then you can sample in n versus n square steps.
This is the Lovaas lifting types of things, you mean?
Yeah. No, I agree with all that. Now, the question whether it's very useful or not for these kind of problems, I don't know. That I don't know. Yeah.
There's no further comments or questions. Please join me in thanking Leticia.
Thank you.
We'll reconvene in half an hour. This break now.